Hello and welcome to another video. This time I'm going to be going through a little bit of solving second order differential equations and then a little bit of proof by induction. Also Aisha, because Aisha sent me these questions, could you tell me where you got the first question from? Because I'm relatively certain that there's no really nice way, A-level way, of solving something like that. I think that's a misprint and that should be 3R. But could you tell me where you got the question from? Because I just want to check. I really do. But I looked at it and I kind of scratched my head yesterday when I was looking at it. And yeah, I couldn't quite see what possible approach might be worth taking. So yeah, let me know if that is a genuine question or if, what's happened there. Just let me know where you've got it from, because I've got a funny feeling that it's just a misprint. Maybe I'm wrong though, because I have been making a lot of mistakes today, so I better be on the ball. Okay, so let's call this Aisha's differential equation. And let's work through it. So what have we got here? We've got essentially a load of blur, but then they just give you this differential equation, which they say you can use, and they want you to show that P is instantaneous for the rest at that point. So let's just solve our differential equation in the normal way, using the characteristic equation. So m plus k squared, you're going to have a minus k squared plus 2k squared equals 0. And then if you go ahead and solve this, you're going to get minus k plus or minus ki. And that's because that equals k squared, but when you move it across, you're going to end up square rooting minus k squared. And the square root of minus k squared is the square root of minus 1 times the square root of k squared, which is ik, plus or minus, yeah? And that's why you end up with this. So this gives us the general solution to the equation, yeah? It's going to be e to the minus kt, a cos kt, plus b sine kt. But we've got some conditions, haven't we? Because we know that the displacement is 0 when the time is 0, and they also give us the initial speed as u, yeah? So we've got those three initial conditions. So I'm just going to run through how that affects things. Let's just plug it in. 0 equals e to the 0 times by a cos 0 is 1, b sine 0 is 0, and so you end up with a equals 0. I was so pleased when I saw that, because that means I can rewrite this as x equals e to the minus kt, well, let's call it b e to the minus kt sine kt. That makes it a lot easier to differentiate. Less work anyway. You're going to get minus bk e to the minus kt multiplied by sine kt. And then when you differentiate the other side, you're going to get k cos kt times by b e to the minus kt. And I'm just going to plug things in again. So this is u when t is 0. Now t is 0 totally wipes out that term. T is 0 here makes cos 0, which is 1. So you end up with k b e to the 0. Well, that means, of course, that b is u over k. And so now we can write down the particular solution to this equation. It is x equals u over k e to the minus kt sine kt. Done. Yeah. Okay, and that's that. Yeah. Now, if I want to know when this is instantaneously at rest, I'll differentiate it. I'm going to get minus u e to the minus kt sine kt. And then I'm going to get over here, when I differentiate this one, I'm going to get k cos kt, but one of the k's are going to cancel with that. So I'm going to end up with u e to the minus kt cos kt. Yeah. Okay, and I'm trying to find when this is instantaneously at rest. So I'm trying to find where the velocity is 0. That's where instantaneously at rest takes place, when the velocity is 0. And I'm going to factorize this bit out, which is never 0. And I'm going to end up with cos kt minus sine kt. Okay, so this is solved when this bracket equals 0. In other words, cos kt equals sine kt. So from that we get tan kt equals 1. And hence kt equals pi. Now, does it just equal pi? Sorry, pi over 4. What am I talking about? Inverse tan of 1 is pi over 4. But is that the only answer you get when you inverse tan? No, you get plus a pi, plus a 2 pi, plus a 3 pi. You can keep adding pi's, can't you, with tan? And so I'm going to put plus n pi, yeah? And therefore kt equals pi times pi, take out the pi, then you're going to have n plus a quarter, just like they've got. And by the way, n is a member of the natural numbers, not the integers, purely because time must be positive. And so they're just making sure that time is positive there by saying n is a member of natural numbers. And that's all there is to it. Okay, the second one, this is quite an interesting proof by induction. You're right, because they will use k and k plus 2 here, because we're only proving this is true for odd integers. So base case n equals 1, yeah? And we're going to have 4 to the power of 1 plus 5 to the power of 1 plus 6 to the power of 1. Well, that equals 15, and so it's clearly divisible by 15. And you're going to assume true for n equals k, just like you always do. Now, the way I prefer to do these, and the book doesn't seem to agree with me, but the way I prefer to do it is to set it equal to a multiple of 15. 4 to the k plus 5 to the k plus 6 to the k equals 15n, where n is a member of the natural numbers, yeah? Okay, now we're going to consider k plus 2, because that will make sure it takes us from one number to the number 2 ahead of it. And if we're starting on an odd number, then that's always still going to be an odd number. And that's why I don't use 2k plus 1 or anything like that, because we just want to show if it's true for 1, then it's true for 3. If it's true for 3, then it's true for 5. If it's true for 5, then it's true for 7, and so on and so forth, like the inductive argument works, basically. And so if I now consider n equals k plus 2, then I'm definitely only going to be working on the odd numbers, because think about how the inductive argument works. It works to show that it's true for n is 1, and then it's showing if it's true for n is k, it must be true for n is k plus 2, in other words, 2 after that number. And that's the clever bit, and I think that's all that you were missing on this question. So what do we have here? We have 4 to the k plus 2, plus 5 to the k plus 2, plus 6 to the k plus 2. Okay, that's the same as 16 times 4 to the k. Now, the reason I've done that is so I can introduce my inductive result. And so now I can say it's 16 times 4 to the k, but that's 15m minus 5 to the k minus 6 to the k. And then I've got plus 5, plus, I know if you don't mind, I'm going to write it like this straight away. 25 times 5 to the k plus 36 times 6 to the k, yeah? And now it's just a case of like keeping it grouped, basically. So minus 16 5 to the k's, but plus 25 5 to the k's, that's 9 5 to the k's, yeah? Okay, that's good. And then here we've got minus 16 plus 36, well, that's 20 times by 6 to the k, yeah? Now, this isn't, on the face of it, obviously divisible by 15 until you consider the prime factor decomposition, yeah? This has definitely got, well, this is clearly a multiple of 15. Let's just write it the other way around to show it. And if I wrote this as 3 times 5 to the k, can you see you've definitely got a 3 times 5 in there? So that's definitely divisible by 15. Similarly for this one, if I write it as 4 times 5 times by 3 times 2 to the power of k, can you see we're going to have a 5 times 3 in there somewhere? And so that's definitely divisible by 15. Yeah, I'm just going to say now, clearly all three terms in, are obviously multiples of 15s, yeah? Let's say are multiples of 15, since they all include a multiple of 3 and 5. Yeah, and therefore it's multiple of 15. Hence, by induction, 4 to the m plus 5 to the m plus 6 to the m is divisible by 15. Okay, maybe I should tighten up my inductive remarks then and say, we have shown it's true for n is 1, and if it's true for n is k, then it's true for n is k plus 2. Hence, by induction, it's true for all the odd integers. And yeah, then you should be fine. Hope that makes more sense. I hope you enjoyed the video and find it useful, Aisha. All the best. Keep up the hard work. You're doing great.